Okay, so good morning, everybody. I am Patrick Tardivel, and today I'm from actually Burgundy University in Dijon, France. And today I'm going to give a talk on the geometry of model recovery by penalized and threshold estimator. And it's a joint work with Thomas Skalski, Piotr Grasik, and also Ulrike Schneider. So first, I consider this optimization problem, this one. And in this optimization problem, we minimize with respect to B the residual sum of squares, so this part, plus a penalty term, so this part. In this problem, X is an n-type matrix, Y is a vector in Rn, lambda is a tuning parameter, a positive tuning parameter, and the polyhedral gauge, the penalty term is a polyhedral gauge. So it's actually a polyhedral gauge. It's just the maximum of a family of linear functions. So in particular, it's a convex function. And you probably know already some polyhedral gauges, for example, the L1 norm, which is really famous penalty term, is a polyhedral gauge. And when actually the penalty term is the L1 norm, we call this optimization problem LASSO optimization problem. You may think about also the supremum norm, which is a particular polyhedral gauge. There is also the sorted L1 norm. For the sorted L1 norm, there is a sequence of parameters, lambda 1 until lambda p, which are these parameters are decreasing. And to compute the sorted L1 norm at B, we start to first order complement of B with respect to the absolute value. And when we use the sorted L1 norm, is this optimization problem here. This optimization problem is called a slope optimization problem. Otherwise, there is also the L1 norm of DB. And so when we use such penalty terms, this optimization problem is called generalized LASSO. And you may also notice that when the kernel, the null space of D is not reduced to zero, this expression is actually just a semi-norm, but not a norm. So we know that the set of minimizer is never empty. But in statistic, Y is random. We would like this set of minimizer a singleton, actually. Y is random, and that's in statistic Y is random, and that's the reason why we would like to find a criterion under which whatever Y, this optimization problem, this one, has a unique minimizer. And now I'm going to give such a criterion, actually. So we have this theorem. So X is still an n-type matrix, lambda a positive tuning parameter, pen is still actually a polyhedral gauge. And we have the following statement. One main peak vector Y, for which this optimization problem, this one, does not have a unique minimizer if and only if this vector space, so it's a vector space spanned by rules of X, intersect the face of this polytope, B stars, and a face for which the dimension is smaller than the dimension of the null space. In general, B stars is a quite polytope, which is, for example, so for the L1 norm, B star is actually the cube. When the penalty term is the supremum norm, B stars is actually the unit ball of the L1 norm. For the L1 norm of DB, then B stars is actually this polytope. And this list is clearly not exhaustive. I may also add, for example, what is B star for the sorted L1 and so on. But I'm going to just focus on few examples. And now I'm going to give actually an illustration of this theorem. So in this optimization, I consider this optimization problem. You may notice that here, the penalty term is actually the supremum norm. Okay, I choose X, the matrix 1, 1. And when X is the matrix 1, 1, you may see that this line is actually the vector space generated by the unique row of X. You may notice that this vector space intersects edges of this polytope. This polytope is the unit ball of the L1 norm. The L1 norm is the dual norm of the supremum norm. Okay, so if I just bring back to the penalty term, you may notice that this statement, the vector space generated by row of X, does not intersect a face whose dimension is smaller than the dimension of the null space. So this statement does not hold, which means that we know that whatever y, this optimization problem has a unique minimizer. And it's that if I take, for example, y equal to, I know that the minimizer of this optimization problem is unique, and I'm going to illustrate that this minimizer is unique. So I call phi this function, and I am going to, by drawing contour line of phi, so here you may observe contour line of phi, then you may observe that the red point is actually the unique minimizer, and it's really a singleton in this case. Now I'm going also to give an example in which the minimizer is not unique. I have the same kind of optimization problem, but the main difference with the previous example is now X is a matrix 1, 0. And when X is a matrix 1, 0, when I draw the vector space spanned by the unique row of X, so it's this line which coincides with the X-axis. You may notice that this line, the X-axis, if you prefer, coincide with actually, not coincide, intersects an edge of this polytope. And thus, here you may observe that in this case, the dimension of an edge is smaller than the dimension of the null space. Thus, this statement occurs. And because this statement occurs, we know that one may pick a vector y for which this optimization problem does not have a unique minimizer. And in particular, when I take y equal to, and when I draw a level line of the function phi like this, you may notice that actually the set of minimizer is a red segment, and it's not a singleton in this case. And now, okay, I'm going to reintroduce probably the heart of this talk, this presentation. It concerns model pattern recovery, and I'm going to explain what I want to do a bit. So I consider a quite famous linear regression model, y equal x beta plus epsilon. So x is an n-type P matrix, beta is an unknown parameter of regression coefficients, epsilon is a random noise, and my objective will be to recover the subdifferential of the penalty term with respect to beta. So first, I'm going to remind what is a subdifferential, and I'm going to explain a bit why actually recovering the subdifferential of beta with respect to a penalty term is relevant. So if I consider I have a function f from Rp to R, mainly I have in mind that f is convex actually. The vector S is actually a subgradient if this inequality occurs. So it means that this, you may see that the affine space is below the curve of the function f. And the subdifferential is a set of all subgradients. So the subdifferential is a set of all elements S which satisfies this inequality. And mainly for convex function, which will be always the case in this presentation, the subdifferential is never empty. And now I'm going to illustrate why actually recovering the subdifferential of beta with respect to a polyhedral gauge penalty term is relevant. So for example, if I consider the L1 norm, then the subdifferential with respect to the is the subdifferential for the L1 norm of x is equal to the subdifferential for the L1 norm at z, if and only if the sine of x is equal to the sine of z. So if I say that I want to recover the subdifferential of beta respect to the L1 norm, it means that I want to recover the sign of beta. Or in other words, if I say that I want to recover the subdifferential of beta with respect to the L1 norm, it means that I want to recover which component of beta are positive, which component of beta are null, and which component of beta are negative. If I consider the supremum norm, I have this equality. So the subdifferential with respect to the supremum norm at x is equal to the subdifferential with respect to the supremum norm at z, if and only if the set of positive components which are maximal in absolute value for x coincide with the set of positive components of z which are maximal, and the set of negative component of x which are maximal in absolute value coincide with the set of negative components of v which are maximal in absolute value. So if I say that I want to recover the subdifferential of beta with respect to the supremum norm, it means that I want to discover which component of beta are maximal in absolute value and positive, which component of beta are maximal in absolute value and negative. I may also consider this penalty term, which is actually total variation of x. And we have this equality. The subdifferential with respect to the total variation at x is equal to the subdifferential with respect to the total variation at z, if and only if the set of positive jumps for x coincides with the set of positive jumps for z, and also the set of negative jump for x coincides with the set of negative jump for z. I may also give, so what's happened for generalized lasso, mainly the subdifferential with respect to this polyhedral gauge, the one which appear in generalized lasso of at x coincide with the set of the first subdifferential at z, if and only if the sign of dx is equal to the sign of dz. And again, this list of examples is not exhaustive. I might add many relevant matrices D. I may also add slope, for which we have some results. And actually, so like I said, I want to recover, it was written here, the subdifferential of beta with respect to the penalty term, which is a polyhedral gauge. And I'm going to give a first condition, actually, a necessary condition. This one. So I remind that we have this optimization problem, and for this optimization problem, this notation represents the set of minimizer, which is never empty, potentially not a singleton. And actually, I said that the subdifferential of beta with respect to the polyhedral gauge pen satisfies the path condition with respect to x and the polyhedral gauge pen when I may pick tuning parameter lambda, I may pick penalized least square estimator at beta, for which the subdifferential of the polyhedral gauge at beta coincides with the subdifferential with respect to the polyhedral gauge at beta. So I have this equality. And now I'm going to see that, so it's when this equality holds, I said that the subdifferential of beta with respect to the polyhedral gauge satisfies the path condition. I'm going to see that this condition is actually necessary for to recover the subdifferential of beta with respect to the polyhedral gauge pen. Yeah, maybe before. First, I'm going to give an example. So I consider this matrix X. I consider this vector beta, and I want to illustrate that actually beta does not satisfy the path condition. So the subdifferential of beta with respect to the L1 norm does not satisfy the path condition, or the sign of beta, because the subdifferential of beta only depends on the sign. The sign of beta does not satisfy the path condition with respect to x and the L1 norm. So to see that, what I did, I may observe that based on this figure. On the x-axis, it's tuning parameters, so lambda, if you prefer. You may observe that X has three columns, so the lasso minimizer has three components, and thus there is one curve for each component on the okay. You may observe also when the tuning parameter lies between 0 and 6.7, something like this, you may observe that the first component is positive, the second component of the lasso minimizer is positive, and third one is null. Thus, when the tuning parameters lie between 0 and 6.7, so the sign of the lasso is positive, positive, and null, and does not coincide with the sign of beta, which is positive, null, and null. Now, if I am between 6.7 and something like 8.3, you may observe that the first component is null, the second component is null, and the third is positive. And then, so when lambda is between 6.7 and 8.3, the sign of the lasso is null, positive, and null, and thus does not coincide with the sign of beta, which is positive, null, and null. And also, if lambda is larger than 8.3, something like this, the lasso minimizer is null, and thus the sign of the lasso minimizer does not coincide with the sign of beta. Okay, so I illustrated based on these figures that actually for this specific beta, for this specific matrix X, the sign of beta does not satisfy the path condition, but actually there is an analytical way to check this condition, and for maybe among you some are familiar with the irrepresentability condition. So I may compute this expression, so where I represents the support of beta and I bar represents the complement of the support. I may compute this expression, and once this expression is larger than 1, which is the case here actually, then the path condition does not hold. And because actually this expression is larger than 1, the path condition does not hold. And that's why, whatever the value of the tuning parameter, I do not recover the sign of beta. Okay. And now I'm going to see that the path condition is actually necessary for to recover the subdifferential of beta with respect to the polyhedral gauge pen. So I remind that Y is a linear regression is a response of the linear regression model. X is an enthalpy matrix, beta is an unknown parameter of regression coefficient, epsilon is random noise, and here I just assume that epsilon has a symmetric distribution. So it's not really a strong assumption. For example, when epsilon is Gaussian with a mean equal to 0, then clearly epsilon has a symmetric distribution. And actually, we have this statement. If the subdifferential of beta does not satisfy the path condition, then the priority to pick at least one tuning parameter lambda, the priority to select penalized least square estimator, for which the subdifferential with respect to the polyhedral gauge pen at beta coincide with the subdifferential of beta with respect to the polyhedral pen is smaller than 1/2. So it's maybe not really surprising, because what I say here, I say that if in the noiseless case, so when y equal x beta, there is no longer epsilon, I fail to recover the subdifferential of beta.
Sorry, Patrick, shouldn't there be a, shouldn't it be the inverse in the
larger than 1/2?
In the irrepresentability condition? Shouldn't it be in the middle there, inside parentheses? Shouldn't it be x transpose x inverse?
You say here, so somewhere like here? Oh, there is, I forget minus 1/2 actually. Yeah, no, it's okay, but I just forget actually the minus 1/2 in this expression. So what I said that if the path condition does not hold, then it means that if I fail to recover the subdifferential of beta in the noiseless case, then the priority to recover the subdifferential of beta when epsilon is no longer 0 is smaller than 1/2. So it's not really surprising. And for people which know the irrepresentability conditions, then actually Based on this theorem, you may recover easily a quite famous theorem of Wainwright, which appeared in the literature maybe 10 years ago, and which claims that as soon as this expression is smaller than 1, then for whatever the value of lambda, the probability is that the sign of the lasso coincident with the sign of beta is smaller than 1/2. I'm going to introduce actually a condition which actually is weaker than the path condition. And I'm going to say that the subdifferential of beta is accessible with respect to x and lambda pen if I may pick a vector y, I may pick a penalized square estimator for which the subdifferential at beta coincides with the subdifferential of beta. And here I'm going to give, I'm just going to give actually analytical characterization. So the subdifferential of beta is accessible with respect to x and lambda pen if and only if for every gamma, as soon as I have this equality, x beta equal x gamma, then the penalty term at beta is smaller than the penalty term at gamma. I have this inequality. And you may observe that actually this characterization does not depend on lambda. So I can say that the subdifferential is accessible with respect to x and lambda pen, or I can say only pen because the tuning parameter does not play any role in this condition. I'm going to illustrate that actually we have the path condition implies the accessibility condition. We have the statement, and actually I'm going to, so path condition is a stronger condition than the accessibility condition. I'm going to illustrate a particular case in which the path condition does not hold, but the accessibility condition holds. So I take the same example as before. When I take X, this matrix, and beta like this, we have already seen few slides before here that actually the sign of beta does not satisfy the path condition. But actually, I may also check easily that as soon as x beta equal x gamma, then the L1 norm of gamma is larger than the L1 norm of beta. Thus, actually, the subdifferential of beta satisfy the accessibility condition. But I can also give a geometric illustration. So here I have still the same matrix X, I have still a vector beta. I just say that the first component of beta is positive and second and third are null. This polytop, this one actually, is the lasso null polytop. So it means that when y lies onto this set, the lasso minimizer is equal to 0. And I did this figure for a specific value of lambda, which is lambda equal 1. And also the green set, when y lies onto the green set, then the first component of the lasso is positive, the second component of the lasso is null, and the third component of the lasso is null. It means that when y lies onto this green set, the sign of the lasso minimizer coincides with the sign of beta. Now, we know that so the second and third component of beta are null. That it means that the mean of y, which is x beta, is generated by the first column of actually of x, and actually the mean of y, x beta, lies onto this dotted line. So in particular, we know that the mean of y is once the mean of y is on this set. In particular, you may observe that the mean of y is out the green set. Then it's not the probability to be in the green set is smaller than 1/2. So in this setting, it means that it's not likely to recover the sign of beta using lasso. You may, but it's quite unlikely. The probability to recover the sign of beta is actually quite weak, smaller than 1/2, clearly. But threshold lasso can do something better actually. So I still consider the same matrix X. Now I consider this vector beta with So first component is really large, the second and third are null, and epsilon has a standard Gaussian distribution. And I have box plots, so you may observe that the first box plot is actually the box plot for the first component of the lasso, the second for the second component of the lasso, and the third. And I still do this figure for lambda equal 1. You may observe that the first component of lasso lies between 12 and 20, the second between 0 and 8, and the third between 0 and 3, something like this. So you may observe that the first component is clearly larger than the second and third. And it means that if you threshold component of lasso, you are going to recover properly. You are going to recover the sign of beta. You are going to identify that the first component is clearly not null, but the second and third are actually not significantly different from 0. And we have actually, now I'm going to give some necessary and sufficient condition for sign recovery by generalized lasso. Okay, so I'm just going to focus on generalized lasso. I consider, and maybe among you, some are know that as soon as we use the L1 norm, we aim at recovering the support of beta, so or even more the sign of beta. But the support of beta is a set of components which are not null. Another example will be using the total variation actually. When you use the total variation of B, when the polyhedral gauge penalty term is the total variation of B, so the L1 norm of this expression, then actually you may recover the jump set. You may recover the component I for which beta I is different from beta I plus 1. And the matrix D, which appear actually in this polyhedral gauge, is actually this one. More generally, when you use actually generalized lasso, you aim at recovering the sign of d beta. Okay, and I'm going to focus on this last actually case because I said that I would like to say that how to recover the sign of d beta. Because if I recover the sign of d beta, it means that here I'm going to recover the set of positive jumps and negative jumps, and thus the set of jumps. In particular, if I recover the sign of d beta, I will recover the support of d beta. And if I recover also the sign of d beta d beta, yeah, if I recover the sign of beta, I recover also the support. And now I say that at beta is a generalized lasso estimator. It will be quite. I want to recover the sign of d beta, so it will be quite natural to try to recover this sign vector using actually this estimator. Okay, and actually, when you use this estimator to recover the sign of d beta, you need the path condition. If the path condition does not hold, the probability to recover the sign of d beta is quite weak. It's smaller than 1/2. But actually, one may relax this stringent condition, stringent path condition, by thresholding component of d at beta. So by this notation, I mean that once a component of d at beta is smaller than tau in absolute value, so tau is a threshold, then we consider this component as equal to 0. And we have actually this statement. Okay, so if the subdifferential of beta is not accessible with respect to x and this polyhedral gauge, then whatever y, whatever lambda, whatever the penalized square estimator at beta, whatever the threshold I use, I am going to fail to recover the sign of d beta. So I have this inequality, which means, yeah, I'm going to fail. I cannot recover exactly the sign of d beta. On the other hand, so I have this sufficient, so it's necessary. I'm going to say there is also a sufficient condition, but which is asymptotic. Say that I have a particular observation of epsilon. And I'm going to construct this yk like this. And you may observe that there is a k beta. Actually, when k is large, it's just a way to say that when k is large means that the signal k beta with respect to the noise epsilon is strong. So yes, it's just this case just allows us to consider asymptotic case in which the signal is really strong with respect to the noise. And actually, if the subdifferential beta is accessible with respect to n and this polyhedral gauge, then for a strong signal, I may pick for sufficiently strong signal, I may pick a threshold for which the sign of this by thresholding component of d at beta, I am able to recover the sign of d beta. And also another way to say that is for when the signal is sufficiently strong, then actually the support of this vector lies onto this nested family of subsets. So, and to construct this nested family of subset, actually I take this vector d at beta, and I order this family of this vector with respect to the absolute value like this. So mainly I say that at the end for generalized lasso, accessibility condition is necessary, and accessibility condition is also sufficient, but at least asymptotically when the signal is strong. I just give in this presentation a result for generalized lasso, but we have also in this article the geometry of model pattern model recovery by penalized and threshold estimator. We have also a result which is valid for any polyhedral gauge, and thus which can be useful if you want to recover the model of the model pattern for of beta when we use a slope estimator or Oscar estimator, for example. Okay. And also, this clearly this theorem is an echo with a similar result I obtained with actually Malgorzata Bogdan, because for with actually in this theorem, the one I obtained with Malgorzata Bogdan, it's just focus on lasso, and the conclusion is similar when the signal to noise ratio is sufficiently strong, and when actually the accessibility condition holds, then by thresholding component at lasso, we may recover the sign of beta. And just to conclude this presentation, I'm going to give actually illustration concerning lasso. I already did with actually, I already obtained with Malgorzata Bogdan. So here, I am going to consider sign recovery by lasso and threshold lasso. So if you want to recover the sign of beta, if you want to use lasso to recover the sign of beta, you need the, in the article with Malgorzata Bogdan, I call it irrepresentability condition. In this article, I would say path condition, it's completely similar. But if you want to recover the sign of beta with lasso, you need this inequality to occur. On the other hand, if you allow to threshold component for lasso, you may even use basis pursuit if you want. Then you may recover the sign of beta under the accessibility condition, or also called identifiability condition in the article with Malgorzata Bogdan. So we need this implication. And as said differently, the path condition implies the accessibility condition. Or also you may say that irrepresentability condition implies identifiability condition are almost similar. And thus, of course, I do not know beta, so it's difficult to check this condition because I do not know beta, but at least I'm able to quantify these two assumptions, irrepresentability condition as well as accessibility condition, at least when X has a standard Gaussian entries. And I mean that depending on the number of non-null components of beta, we know whether or not these two conditions hold. So here I consider 100 times 300 standard Gaussian matrix. On the x-axis is the sparsity, the number of non-null components of beta, so between 0 and 60. The y-axis provides the probability that beta satisfies the identifiability condition or irrepresentability condition, or you may also say path condition and accessibility condition. So in particular, in red, it's the probability, depending on the number of components of beta, that beta satisfies the irrepresentability or path condition. You may observe that when actually the sparsity is smaller than 9, yes, this probability is almost 1. When it's larger than 1, this probability is close to 0. And actually 9, the value of 9 is given by this expression. So here, it's the number of rows divided by 2 times the number log of the number of columns, which give approximately 9. And for the identifiability curves, so it gives probabilities that beta satisfies the identifiability condition or equivalently the accessibility condition. So when the sparsity is smaller, when the number of non-null components is smaller than 31, this probability is close to 1. When it's larger than 31, this probability is close to 0. And actually, this value of 31 is given by using actually the transition curves of Dono and Tanner. And finally, we did actually some numerical experiments. It was actually a numerical experiment we conducted with actually Malgorzata Bogdan. So we still consider the linear regression model. We have still actually the design matrix is entries of the design matrix are still standard Gaussian entries. Epsilon is a standard as a standard normal distribution, and we consider the case in which beta has 20 non-null components. So when beta has 20 non-null components, we are here. So clearly, the path condition, we are exactly here, so the path condition does not hold. And because the path condition does not hold, I just remind this statement. The probability of sign recovery is smaller than 1/2, theoretically. But in practice, it's much, 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 much smaller than 1/2. It's almost 0. So it means that clearly with LASSO, we are going to fail to recover the sign of beta. But the accessibility, we are k equal 20, the accessibility condition or identifiability similar condition holds. Thus, this statement holds. The sign of beta is accessible with respect to x and the L1 norm when k equal to 20, the sparsity equal to 20. So we know that for a sufficiently strong signal, by thresholding component of LASSO, we are going to recover the sign. And that's what we are going to illustrate here. So here, on the x, so non-null component of beta are all equal to t. Yeah. What we have also on the y-axis is the probability of sign recovery, exact sign recovery. And so you may observe that when when t is large, it means that the signal to noise ratio is large. And you may observe that when the signal to noise ratio is large, then the probability of sign recovery by thresholding LASSO as well as by thresholding basis pursuit is actually really close to 1. It means that thresholding LASSO or thresholding basis pursuit succeed to recover the sign of beta. And it's my last slide, so thank you for listening. And mainly, this talk was based on this article, which is the first version of this article, but not the final one, is actually available online. But also there is some related articles, one with my colleagues, Malgorzata Bogdan, and also another one with my colleague, Ulrike Schneider. And if you have question, I can reply your question. Thank you.